Good afternoon, everyone. So myself Devyani, I am dealing fluid mechanics and hydraulic machine subject for this GATE class. So yesterday we have discussed about properties of the fluids and the effect of jet acting on the vanes. And now we are going to discuss about the flow through pipes related to the different types of flows like laminar flow and turbulent flow, and also the dimensional analysis. So coming to the first topic of flow through pipes. So, first of all, let us know the nature of flow. The flow in pipes will generally be under the pressure when comparing with the atmospheric pressure. Usually, the actual pressure or the external pressure acting on the water will be more when comparing with the atmospheric pressure. Whether a flow is laminar or turbulent or transition. So, whatever it is, all the types of flows are mainly depends upon the Reynolds number. So the Reynolds number is denoted with R suffix E, and it is defined as it is the ratio of inertia force to viscous force. So inertia force is the product of mass and acceleration. So we can write the expression for inertia force. So if we take the mass in terms of mass density, then we can write mass density is nothing but mass density is denoted with rho. So we can write it as rho equals to mass by volume. So from that equation, we can take mass, then the equation will be mass equals to density into volume. So we can write this equation as mass as a rho into density into volume, and we know that acceleration is denoted with A. So we can write the acceleration as velocity by time. So if we simplify that equation, the total equation for mass and acceleration, then we can get the final equation as rho L square V square. So rho A V square can be written as rho L square V square. Then the another one is viscous force. So viscous force is the product of shear stress and area. So we can write it as we know that the equation for shear stress is tau equals to mu into du by dy or mu into v by L. So here mu is the dynamic viscosity, v is the velocity, and L is the dimension. And multiplying with the area can written as L square. So length into length can be the area. So the final equation for the viscous force is mu L V. So substituting all these forces, the inertia force and viscous force in the formula of Reynolds number, then it will be Reynolds number Ra equals to inertia by viscous force. So simplifying the equation, we get rho L V by mu. In case of pipes, the L is replaced by the diameter, then the equation will be Re equals to rho V d by mu, or so rho by mu, we can write it as 1 by mu. So mu by rho is equals to kinematic viscosity in mu. So we can write this equation as Vd by mu also. So coming to the laminar and turbulent flow. So usually the laminar and turbulent flow was mainly depends upon the Reynolds experiment. So Reynolds conducted an experiment to find out the different types of flows. So to determine the types of flows, he has taken a colored dye having the same specific weight as of water, and which is used to study the flow pattern. If the velocity is small, the dye injected in the water remained in the form of a straight and stable filament passing through a glass tube. So steadily that is selected as the laminar flow. And if the force was increased, the velocity was increased, after a critical state, the filament of dye shows the irregularities and begin to waver. So we can consider that type of flow as the turbulent flow. The head loss in a certain length of the pipe of constant diameter can be determined by plotting the HF by L versus V, and that can be shown as the log-log plot. So this is the plot for the HF by L versus V for the log-log plot. So if we draw the graph for these two values for different types of flows, then we can get the diagram starting from 0 to A to B, B to C, like this. So here A is the lower critical point, B is the higher critical point, C is the limit of transition. And at these points, the slope at the point of C, the slope N is 1.75, and beyond the C, the slope is 2. So we can say that n equals to 2 usually for the rough wall pipes and n equals to 1.75 for the smooth wall pipes. So if the flow was varies from 0 to A, then it is laminar flow. If it is varies from A to C, then it is transition flow. If the flow is beyond C from the graph, then it is turbulent flow. So like that, we can find out the different types of flows by using this graph. And also, we can find out the Reynolds number value from the graph, as if the Reynolds number is less than 1000, then it is laminar flow. If the Reynolds number is in between 2000 to 4000, then it is transition flow. If the Reynolds number is greater than 4000, then it is turbulent flow. So like that, we can identify the different types of flows. For critical Reynolds number, critical Reynolds number is the 2000 and upper critical Reynolds number is about 2700 to 4000. And we have to remember one thing, that the lower critical Reynolds number of flow of fluid in pipe or corresponding to point A is greater engineering importance. So from this figure, we can get the relation, that is for the head loss, HL proportion to is directly proportional to velocity, that is n equals to 1 for the laminar flow. And for the head loss, HL is directly proportional to B power n, that is n equals to 1.75 for the turbulent flow of smooth pipes. And the head loss HL is proportional to B power n, that is n equals to 2 for the turbulent flow of rough pipes. The next topic is losses in pipes. If the fluid flow through a pipe, there is a resistance will take place due to the flowing fluid. So resulting that resistance, a loss of energy will take place. And this loss of energy will be classified into two types, major loss and minor loss. Major loss was mainly due to the friction and minor loss was mainly due to various fittings, transitions, change in velocities to change in the cross sections, etc. So coming to the loss of fluid friction for laminar flow, the losses which were considered of for the fluid friction for a laminar flow are, if the frictional resistance in the laminar flow, frictional resistance is denoted with small f. The frictional resistance in the laminar flow is proportional to the velocity of flow. The frictional resistance F should be independent of the pressure. The F should be proportional to the area of surface in contact. The frictional resistance F is independent of nature of the surface in contact. The frictional resistance was greatly affected by the variation of the temperature of the flowing fluid. So these are the different laws were considered for laminar flow. Then the loss of fluid friction for turbulent flow. The loss of fluid friction for turbulent flow is the frictional resistance in case of turbulent flow is proportional to velocity power n, where the index n varies from 1.72 to 2. So for smooth pipes, the value n is 1.75. For rough pipes, the value is 2. And this frictional resistance is independent of the pressure. The friction resistance is proportional to density of the flowing fluid, and this friction resistance is slightly affected by variation of the temperature of the flowing fluid, and this frictional resistance is proportional to area of surface in contact, and this frictional resistance depends on the nature of the surface in contact. So these are the main laws to be remembered in case of the turbulent flow. So coming to the major loss of head, the major loss can be find out by using the basic equation, that is Darcy-Weisbach equation. So from that Darcy-Weisbach equation, the major loss of the head HF is having the formula, that is HF equals to FLV square by 2ZD. Here L is the length of the pipe of the diameter D, V is the mean velocity of the pipe, F is friction factor, and which is a function of the Reynolds number and the relative roughness. Here the ratio of HF by L is equal to SF, S suffix F. Here S suffix F represent the energy slope, which is equal to the hydraulic gradient in uniform flow. In long pipelines, the head loss due to friction forms a major part of the total loss acting on the pipe. Hence, this loss is considered as the major loss of the pipe. The head loss due to friction is considered as the major loss of the pipe. This equation is derived based on the experiments of Froude, and which revealed that the frictional resistance varies approximately with the square of velocity. The frictional resistance varies with the nature of the surface. So the next topic, minor losses in the pipes. So minor losses in the pipes may cause mainly due to different situations, and those situations are the minor loss causes due to sudden expansion, due to sudden contraction, at the entrance to a pipe from a reservoir, at exit of a pipe, and due to conical expansion, due to bendings and due to pipe fittings, and due to an obstruction to the flow. So if the minor loss is due to sudden expansion, then the head loss can be calculated by using the formula, that is V1 minus V2 whole square by 2Z, or V2 square by 2Z into A1 minus 1 whole square by A2. So this is the figure showing the sudden expansion. The velocity changes from V1 to V2. Then for sudden contraction, the equation is 1 by Cc minus 1 whole square into V2 square by 2Z, or it may be nearly equals to 0.5 V2 square by 2Z. So this figure shows the sudden contraction. So this is the vena contracta, where the velocity was contracted at this point. So this point is called as the vena contracta, and this is the velocity at vena contracta V suffix C. Then at entrance to a pipe from a reservoir, the velocity, the head loss is 0.5 V2 square by 2Z. And at the exit of the pipe, the equation is, the head loss equation is V square by 2Z. For a conical expansion, the equation is K into V1 minus V2 whole square by 2Z. Here K is a constant. For bends and for pipe fittings, the equation is K into V square by 2Z. And here also K is the constant. If any obstruction was occurred, then the equation will be HL equals to A by Cc into A minus 1 of whole square into V square by 2Z. Here Cc was lies between 0.6 to 0.666. So this is the figure showing the obstruction to flow. The next topic is hydraulic gradient line. Hydraulic gradient line was mainly depends on the different types of the heads, like pressure head, velocity head, and datum head. So whereas the hydraulic gradient line can be defined as if the pressure head at different sections of pipe are plotted to a scale as vertical ordinates above the axis of pipe, and all these points are joined by a straight line. In a straight line sloping line will be obtained, and that line is known as the hydraulic gradient line. So at any section of the pipe, the vertical distance between pipe axis and the hydraulic gradient is equal to pressure head at that section. So it is also known as pressure line. This hydraulic gradient is also known as the pressure line. Another one, hydraulic gradient line for the inclined pipe. So in case of inclined pipe, the Z, the height of the pipe axis at any section above the arbitrary datum, then the vertical height of the hydraulic gradient above the datum at section pipe represents piezometric head, and which is equal to pressure head plus datum head. So in such case, it is called as the piezometric line. So in case of inclined pipes, usually the velocity of head will be considered as 0. Hence only the pressure head and the datum head will be obtained to find out the inclined pipe. Hence the piezometric line is taken to calculate the piezometric head, that is PW, P by rho Z plus Z. Another topic is total energy line. So if a different section of the pipe, the total energy in terms of the head is plotted to scale. The total energy or total head is the sum of pressure head, velocity head, and datum head. Or in case of the total energy, so total energy is the sum of pressure energy, kinetic energy, and potential energy. So the total energy is plotted to a scale as vertical ordinate above the datum, and all the points are joined, then it will get a straight line sloping. So that straight line is called as the total headline or total energy line or energy gradient. So the total energy line will be at a vertical distance equal to V square by 2Z above the hydraulic gradient. So hydraulic gradient line consists of only pressure head and datum head. So If this hydraulic gradient line was included with the velocity head, then it becomes as total energy line. That was the main difference between hydraulic gradient line and total energy line. So we have to remember one thing, that the hydraulic gradient line may even rise in the direction of the flow when flow passes from narrow to the large pipe. Since the velocity in large pipe is smaller when comparing with the smaller pipe. Consequently, the pressure in larger pipe is more when comparing with the smaller pipe. But while coming to the total energy line, the line will not rise in the direction of the flow, not like the hydraulic gradient line. In total energy line, this line will not rise into the direction of the flow, since there is always a loss of energy in the direction of the flow will takes place. So due to that, the line cannot rise up to the direction of the flow. So unless there exists some devices such as pump in the pipe system which add energy to the flowing liquid. Next one, pipes in series or compound pipe. So if a pipeline connected to two reservoirs is made up of several pipes of different diameters like D1, D2 and D3 etc. and the lengths L1, L2 and L3 etc. all connected end to end, then the system is called as pipes in series. So like this, if one pipe is connected to the another pipe, then this arrangement is called as the pipes in series. And in this case, the difference in liquid surface levels in the two reservoirs is equal to sum of the head losses in all the sections. So to calculate the difference of the head in the two reservoirs, the formula will be sum of the head losses in the all sections. That is the difference of the head levels, H equals to HF1 plus HF2 plus HF3 plus and so on. So HF1 is the head loss due to friction at first pipe, that is F1 L1 V1 square by 2Z D1 plus HF2 is the head loss due to friction in second pipe, that is F2 L2 V2 square by 2Z D2. Here F1 is the friction factor in first pipe, L1 is the length of the first pipe, V1 is the velocity in the first pipe and D1 is the diameter of the first pipe. Similarly F2 L2 V2 D2 and so on. And so this is the head loss in between the two reservoirs. And the discharge through each pipe can be calculated. Usually the discharge in each pipe will be same. If the pipes are arranged in series, the discharge in each pipe will be same. And the discharge can be calculated by using the formula area into velocity. So the area at first pipe into velocity at first pipe, and which is equals to area at second pipe into velocity at second pipe, that is A1 V1 equals to A2 V2. So we can write it as pi D1 square by 4 into V1, and which is equals to pi D2 square by 4 into V2, and which is equals to pi D3 square by 4 into V3, so on so. Then equivalent pipe. A compound pipe consisting of several pipes of varying diameters and length is to be replaced by a pipe of uniform diameter, and which is known as the equivalent pipe. So all these pipes to be replaced to the uniform diameter pipe, then that formation is called as the equivalent pipe. The uniform diameter of equivalent pipe is known as the equivalent diameter. So this can be calculated by using the formula, that is 1 by d power 5 equals to L1 by d1 power 5 plus L2 by d2 power 5 plus L3 by d3 power 5 plus and so on. Here L1 is the length of the first pipe, D1 is the diameter of the first pipe, L2 is the length of the second pipe, and D2 is the diameter of the second pipe, and so on. The next condition is pipes in parallel. If the pipeline divides into two or more parallel pipes which again join together at a downstream side and continue as a main line, then the pipes are said to be parallel. So the pipes are connected in parallel in order to increase the discharge passing through the main. So usually in case of series condition, the discharge is constant, but in case of parallel condition, the discharge will be increased from one pipe to another pipe. So to increase the pipe, to increase the discharge of the flow, the pipes should be connected in parallel. So here the formula for that one is Q equals to Q1 plus Q2 plus and so on. And in case of pipes in parallel condition, the head loss is constant, not like the pipes in series. In case of parallel, the head loss is constant. That is HF equals to F1 L1 V1 square by 2Z D1 equals to F2 L2 V2 square by 2Z D2, and which is equals to and so on. And here we have to remember one thing, that if there are n pipes of same diameter laid in parallel in place of single pipe, then the diameter of each parallel pipe can be calculated by using the formula, that is small d equals to capital D by n power 2 by 5. Here small d is the diameter of each parallel pipe, capital D is the diameter of single main pipeline, and n is the number of parallel pipes. Then discharge through the branched pipes. So usually the discharge through the branched pipes can be possible if the datum ZD is greater than Z2 and Z3. If these two datums are more than the less than the ZD, then only these can be possible. So if we send the tank of the water, A tank water to B and C, then definitely the datum, the total head should be more than the datum of the C pipe and C branch and B branch. Then only we can send the water and the water can easily flow towards the B and C. The basic equations like continuity equation, Bernoulli's equation and Darcy-Weisbach equations are used in the analysis of discharge through branched pipes. And we have to remember one thing, that at any junction, according to continuity equation, the total rate of flow towards the junction is equal to the total rate of flow away from the pipe. So let's discuss some bits regarding these flow through pipes. So the first one is the loss of head due to sudden expansion of a pipe is given by HL equals to V1 minus V2 whole square by 2G. So this is the equation for head loss due to sudden expansion. Another question. The loss of head due to sudden contraction of a pipe is equals to, usually the formula is, I will show the formula. So the formula is 1 by Cc minus 1 whole square into V2 square by 2Z. So that is the formula. Here this formula is 1 by Cc minus 1 whole square into V2 by 2Z, and this one is 1 minus 1 by Cc whole square into V2 by 2Z, and this one is 1 by Cc into 1 minus V2 square by 2Z. But what is the formula? 1 by Cc minus 1 whole square into V2 square by 2Z. So we should get for the square for this term and for this term also. So here it doesn't have that equation, so the answer is none of the above. Formula is 1 by Cc minus 1 whole square into V2 square by 2Z. Then another question. The hydraulic gradient line HGL represents the sum of pressure head and datum head only. Only for the total energy line we get all the heads like pressure head, velocity head and datum head. But for hydraulic gradient line, it is the sum of pressure head and datum head. So here we get the total energy line represents the sum of pressure head, kinetic head and datum head. Another question. When the pipes are connected in series, then the total rate of flow will be constant. So we have to remember that one. For the series, the discharge is constant. For the parallel condition, the head is constant. So here the answer is the discharge is same as flowing through each pipe. Here the discharge is constant for each and every pipe. Another question. The power transmitted through pipes will be maximum when the head loss due to friction is equals to 1/3 of the total head at the inlet of the pipe. So the power transmitted through each pipe will be maximum when the head loss due to friction is equal to 1/3 of the total head at inlet of the pipe. Another one, the valve closure is said to be gradual if the time required to close the valve is T is greater than 2L by C. So here L is the length of the pipe, C is the velocity of the pressure gradient. The velocity of pressure wave in terms of bulk modulus and density is given as, so already we have discussed this one, right? So the velocity of the pressure wave in terms of bulk modulus and density is given as C equals to square root of K by rho. The velocity of the pressure or the velocity of the sound, C equals to square root of K by rho. Then next one, the Reynolds number is defined as the ratio of inertia force to viscous force. Reynolds number is defined as the ratio of inertia force to viscous force. Then next topic, so now we are going to discuss about the next topic, that is dimensional analysis. So usually the dimensional analysis is a method to find out the physical phenomena by dimensionally correct equation among certain variables which affect the phenomena, and it reduces the number of variables and arranges them into dimensionless groups, useful for the phenomena which for the analytical solutions and must be solved experimentally also. So the fundamental dimensions are mass denoted with m, length denoted with L, and time denoted with T, and the temperature denoted with Q. So in place of mass, the force is also considered as a fundamental quantity. So coming to dimensional homogeneity, the dimensional analysis is based on the Fourier principle of dimensional homogeneity. An equation is said to be dimensionally homogeneous if the form of the equation does not depend upon the units of measurement. Then only we can find out then only we can say the equation as a dimensionally homogeneity. So to satisfy this condition, the dimension of each side of equation must be same. So if we take a continuity equation, that is Q equals to A into V, then the units of the discharge is meter cube per second. Then in right side, area has the units meter square and velocity has the units meter per second. So by multiplying these two, we get meter cube per second. So on the left side and the right side, the units are same, and as well as the dimensions also same. So we can say this kind of equation as the dimensionally homogeneous equation. So similarly, we have the another one, that is hydrostatic law of pressure, P equals to gamma H. And Newton's second law, that is F equals to ma, and another one, P equals to 32 mu v into L by d square. Then another equation, P pressure equals to F into Ip into v square by 2d, and T equals to 2 square root of 1 by g. Another equation, V equals to U plus At. Another equation, Q equals to 2 by 3 CD into square root of 2z L into h power 3 by 2. So all these equations are considered as the dimensionally homogeneous equations. Why? Because the left side dimensions are equal to the right side dimensions. Hence, we can call this kind of equations as dimensionally homogeneous equations. Whereas while coming to dimensionally non-homogeneous equations, the equations are P equals to 4.75 root Q. Here P is the pressure, has the units Newton per meter square, and Q is the discharge, has the units meter cube per second. So the left side units and the right side units are not same, hence the dimensions are also not same. And the next one is P equals to 500 H and F equals to 50 A, and V equals to 10 into square root of Rs, and V equals to 1 by N R power 2 by 3 into S power 1 by 2. Then V equal to C into square root of Rs, V equals to 0.85 into Y power 0.64. So these are the Chezy's formulas and Manning's formulas, and V equals to U plus 9.84 T, and Q equal to 1.7 L H power 3 by 2, etc. So all is considered as a dimensionally non-homogeneous equations. So the empirical equations involving the numerical coefficient are dimensionally non-homogeneous equations only. The methods of dimension analysis are simply based on the condition that the total number of variables should be equal to the number of independent variables plus one dependent variable. So to find out the dimension analysis, to go for the method of dimension analysis, the fundamental condition is total number of variables should be equal to number of independent variables plus one dependent variable. So for this method of dimension analysis, we have mainly two methods, that is Rayleigh's method and Buckingham-Pi theorem method. So coming to Rayleigh's method, so Rayleigh's method gives a special form of the relation among the dimensionless groups. So but drawbacks for this method is It does not provide any information regarding number of dimensionless groups to be obtained as a result of dimension analysis. And another drawback is the method becomes rather cumbersome when a large number of parameters are involved. So that we can go for the Buckingham pi theorem method. So this method consists of repeating variables. Hence, we can call this method also as the method of repeating variables. It offers an advantage over the Rayleigh's method in advance of the analysis to how many dimensionless groups are to be expected. So this method expresses the equation in terms of dimensionless groups, that is in terms of pi terms. The number of pi terms should be equals to n minus m. Here n is the total number of variables and m is the number of repeating variables. The selection of repeating variables has three conditions. The first one is a variable describing geometry of a flow such as diameter and length. And second one is it should be a fluid property like viscosity, density, surface tension, elasticity and vapor pressure. And the third condition is the variable characterizing the fluid motion. Example, velocity, acceleration and discharge. So by using these repeating variables, we can find out the number of pi terms, and using the number of pi terms, we can find out the dimensionless parameters. And we should remember one thing, that the nature of form of the dimensionless pi terms would entirely depend upon the selection of repeating variables only. Another another topic is model and prototype, the very important topic. So prototype is the full size machine, and it is the actual machine which was existed in the site. And model is the tool for studying the behavior of a prototype. So it may be a larger or smaller or even the same size as the prototype also. Another topic, types of similarities. So for complete similarity to exist between the model and its prototype, it is necessary that it must be geometrically, kinematically and dynamically similar. So coming to the first one, the geometrical similarity. The similarity of shape, to satisfy this condition, the ratio of the corresponding length in the model and its prototype must be same. That is, the length of the prototype by length of the model should be equals to width of the prototype by width of the model, and which should be equal to diameter of the prototype by diameter of the model. And this ratio is also known as the scale ratio or scale factor. And then kinematic similarity. So the similarity of motion is also, kinematic similarity is also known as similarity of motion. The streamline pattern in model must be same as that in its prototype. The ratio of kinematic quantities representing flow characteristics such as time, velocity, acceleration and discharge must be same at all corresponding points. So that is, the time scale ratio T suffix R should be equals to prototype time by model prototype. And similarly, velocity ratio V equals to Vp by Vm, that is velocity prototype by velocity model, velocity of the model. And acceleration ratio A suffix R equals to acceleration prototype by acceleration model. And similarly for discharge also. So coming to the third one, dynamic similarity. The corresponding forces have the same ratio throughout the flow field. That is, similarity of forces is called as the dynamic similarity. And we should remember one thing, that for either dynamic or kinematic similarity to exist, geometric similarity is a prerequisite. So whatever it is a kinematic or dynamic. The geometric similarity is the prerequisite condition for these two similarities. If two flow fields are dynamically similar, they are necessarily kinematically and geometrically similar also. The various force ratios, the next topic is various force ratios. So the various force ratios are having some names. So these names are called as the dimensionless numbers. So the dimensionless numbers are the Reynolds number, Flood number, Cauchy number, Weber number, Euler number, Max number, etc. Coming to first one, Reynolds number. Reynolds number is the ratio of inertia force to viscous force. So the formula is rho v L by mu. Significance of this Reynolds number is it completely submerged flow. That is for airplanes and torpedo, etc. And this significance, completely submerged flow. So airplanes for flow through pipes and plates. So another significance is viscous flow. Setting of particles, fluids, flow in flow meters in pipes like venturimeter and or phase meter, etc. So coming to the next dimensionless number, Froude's number, and it is the ratio of inertia force to gravity force. So it can be written as V by square root of Gy or Gd. This significance is for open channel flow where free surface is present, wave action as in breakwaters and ships, hydraulic structures such as spillways, stilling basins, weirs and notches, forces on bridges, bridge piers and offshore structures. So for all these conditions, the Froude's number is very, very useful. Another number is Euler's number. Euler's number is nothing but it is the ratio of inertia force to the pressure force. So the equation is V by square root of 2 into delta P by rho. So it is derived from the ratio of inertia and pressure forces. So it is the reciprocal of Euler number. The reciprocal of Euler number is called Newton number. And the significance is in cavitation studies, the pressure force is important in addition to the viscous force, and the dynamic similarity will be obtained when the Reynolds and Euler number are kept the same for model and prototype. So the next number is Cauchy number. Cauchy number is the ratio of inertia to elastic force, and the equation is V squared by E by rho. And another number is Mach number. So it is the ratio of inertia force to the elastic force, and so we can write it as stream velocity by acoustic velocity in the field. So we can write the equation as V by square root of E by rho. So it is also the ratio of inertia force to elastic force. And the another one is Weber number. So Weber number is the ratio of inertia force to surface tension force. So the equation is rho V square L by sigma. So surface tension is denoted with sigma. And the significance is in formation of water droplet or bubbles, the flows of a shallow depth over spillways, dams, etc. for dynamic similarity to exist between a model and prototype. Hence, the Weber number can be written as similarity can be written as Reynolds number of prototype should be equal to Reynolds number for the model. Froude's number for prototype should be equal to Froude's number for the model. Similarly for all the numbers, and all is depending on the significance of various forces only. So the similitude scale ratios for individual parameters. So we have the scale ratios. Coming to the parameter, the geometric parameter length, the dimension is L, the Froude law is LR, and the Reynolds law is also LR as the scale ratio. For area, the dimension is L square, for Froude law it is LR square, and for Reynolds law it is LR square. For volume, the dimension is L cube, Froude law is LR cube, and the Reynolds law is also LR cube. Now coming to the kinematic parameters, the velocity has the dimension L t power minus 1. The scale ratio from the Froude law is square root of LR. The scale ratio from the Reynolds law is mu r by LR into rho r. Then for time, the dimension is T. The scale ratio for Froude law from the Froude law is square root of LR, and the Reynolds law from Reynolds law, the scale ratio is LR square into rho r into mu r. Then for acceleration, the dimension is L t power minus 2. From Froude law, the scale ratio is 1. From Reynolds law, the scale ratio is mu r square by rho r square into LR cube. Then for discharge, the dimension is L cube into T, L cube into t power minus 1 usually. And for from Froude law, the scale ratio is LR power 5 by 2, and Reynolds from Reynolds law, the scale ratio is LR mu r by rho r. Then coming to the dynamic properties, the mass has the dimension m, and from Froude law, the scale ratio is LR cube into rho r, and for Reynolds law also, the scale ratio is LR cube into rho r. For force, the dimensions are ml t power minus 2. From Froude law, the scale ratio is LR cube into rho r. From Reynolds law, the scale ratio is mu r square into rho r. For pressure, the dimensions are m L power minus 1 t power minus 2. The Froude law has the scale ratio. From Froude law, the scale ratio is LR into rho r. From Reynolds law, the scale ratio is mu r square by LR square into rho r. For the momentum, the dimensions are ml to power minus 1. And from Froude law, the scale ratio LR power 7 by 2 into rho r. From Reynolds law, the scale ratio is LR square into mu r. For energy of work, the dimensions are ml square t power minus 2. The Froude law is L r power 4 into rho r. From Reynolds law, the scale ratio is L r mu r square by rho r. And the final one, power. For power, the dimensions are ml square t power minus 3. From Froude law, the scale ratio is L r power 7 by 2 into rho r. From Reynolds law, the scale ratio is mu r cube by L r into rho r. So these are the different scale ratios for Froude's law and Reynolds law for different parameters like geometric, kinematic, and dynamic properties. And the next topic is types of models. So usually for the hydraulic, these hydraulic models are classified into two types, that is undistorted models and distorted models. Undistorted models means undistorted model is which is geometrically similar to prototype and it will have a perfect similitude. Then coming to distorted model, one or more terms of model are not identical with their counterparts in the prototype. So the distortion may be of either geometrical or material or hydraulic or a combination. Example, okay, recording. Example, in reverse, vertical scales are generally greater than the horizontal scales. Hence, rivers are considered as the distorted models and the oceans or even the small models are considered as the undistorted models which were existed in our laboratories. Another topic is scale effect. So, in complete similitude does not exist between model and its prototype. The discrepancy or a disturbing influence is called as the scale effect. Usually, we never face the similarity between the model and prototype. There is something, a small minor error may take place. So that error is considered as the scale effect. If in a particular problem, both gravity and viscous forces are predominant, then for complete similarity to exist between the model and its prototype, both Froude as well as Reynolds necessary model laws should be satisfied simultaneously. For this, the necessary condition should be satisfied is Lr whole power 3 by 2 is equals to gamma r, where gamma is the kinematic viscosity and example is for partially submerged objects. So let's discuss some of the problems in dimension analysis. So the problem is in a 1:50 model of a spillway, the discharge was measured to be 0.3 meter cube per second. The corresponding prototype discharge in meter cube per second is, so for this one, the solution is, as gravitational force is predominant, the Froude model law has to be applied. So here for model and prototype, the gravity is same. Hence, the Froude's number can be written as Fr equals to V by square root of Gy. Here G is same for the model and prototype. Hence, the similarity between model and prototype for Froude's number can be written as Vm by square root of Ym equals to Vp by square root of Yp. Here G for the model and prototype is same. So here we have, and then this equation become as, so Vr is nothing but Vm by Vp, the model and prototype ratio, and which is equals to Ym by Yp, and which is equals to square root of Lr for the Froude's model. And we know that discharge ratio Qr equals to area ratio into velocity ratio. So we can write it as length scale ratio power 2.5. So if from this equation we can write discharge ratio is nothing but ratio of the model and prototype. So we can write it as, here we have 1/50 for the model. They have given the measurement as 1/50. The ratio is given as 1/50 whole power 2.5. So substituting all the values for the model and prototype in this equation, that is Qp equals to Qm by Lr power 2.5. Then we get Qp equals to 5303. The discharge for prototype is 5303. Another problem, the height of a hydraulic jump in the stilling pool of a 1.25 scale model was observed to be 10 centimeter. The corresponding prototype height of the jump is, so it is a simple one. They have given the scale ratio and they have given the model height. Simply based on that, we have to find out the prototype height. So for that, we go through the ratio, that is height for model by height for prototype is equals to scale ratio. So already we have the scale ratio as 1 by 25. So substituting that, we can get HP equals to 25 into HM. So from there we can get the height of the prototype as 2.5 meters. Another problem, a river reach of 2 km long with a maximum flood discharge of 10,000 meter cube per second is to be physically modeled in the laboratory, where maximum available discharge is 0.2 meter cube per second. For a geometrical similar model, based on equality of Froude number, the length of the river reach in the model is, so here we have to find out the length of the model based on the Froude's number. So they have given the prototype values like length of the prototype, discharge of the prototype, and they have given the discharge of the model. So simply by using the condition for discharge, that is discharge ratio by discharge for model by discharge for prototype equals to LR power 2.5. So substituting the values, we can get LR equals to 0.01319. And we know that LR is length of the model by length of the prototype. And from there, we can find out the length of the model as 26.4 meters. Another problem, the height of hydraulic jump in a stilling pool of 1:25 scale model was observed to be 10 centimeter. The corresponding prototype height of the jump is, so simply we have both the values, the ratio and the model height. So substituting both the values, that is 10 into 25, then we get the prototype height as 2.5 meters. Another one, which one of the following statement is not correct? So first, let's discuss. The models are always smaller than the prototype, of course, usually. So models are always smaller than the prototypes. So it's not the correct one. Why? Because models are maybe equal to the prototype or even more than the prototype also. So models are always not smaller than the prototypes. Another one, dynamic similarity between the model and the prototype can be verified by equating Reynolds number in a viscous flow, of course. So it is true. Another one, Mach number achieves significance when the velocity of fluid approaches or exceeds the sonic velocity. So Mach number was mainly depends on the sound. So that is C equals to K by rho. So definitely it was the correct one. And the third one is distorted models are always exaggerated on a vertical scale, of course. So distorted models are only on the vertical scale, but not on the horizontal scale. So all the B, C and D are correct, but not the A1. So A1 is the not a correct one. Another question, distorted models are needed for rivers, dams across wide rivers and harbors. So of course, distorted models are needed for rivers, dams and for harbors also. So we need all. Okay. So up to this, we have completed this topic. In the next session, we will listen the remaining.